Welcome to this gentle exploration of one of the most mysterious and beautiful territories that human knowledge has ever discovered. Tonight, we drift into the realm where information itself takes on an almost magical quality, where the very foundations of reality reveal themselves to be far stranger and more wonderful than we could have ever imagined. There is something almost musical about the way quantum computers work, a symphony played not with instruments, but with the fundamental particles of existence themselves. Picture, if you will, stepping across an invisible threshold, leaving behind the familiar world where things are definitively here or there, on or off, true or false. In the quantum dreamscape, we enter a place where a single piece of information can exist in multiple states simultaneously, where particles separated by vast distances can influence each other instantaneously, and where the very act of observation changes the nature of what we observe. It is both humbling and beautiful that this technology, which may reshape our entire civilization, operates according to principles that challenge our most basic intuitions about reality. In our everyday experience, an object is in one place at one time. A coin shows either heads or tails, never both. A light switch is either on or off. These seem like the most fundamental truths of existence, as reliable as the sunrise or the rhythm of our breathing. Yet quantum computing invites us into a deeper layer of reality, where these certainties dissolve into clouds of probability, where information itself becomes a fluid, dancing entity that can be everywhere and nowhere all at once. The quantum computer doesn't simply process information, it choreographs a ballet of possibilities, allowing computation to unfold in ways that mirror the mysterious workings of the universe itself. This is why quantum computing awakens both fascination and a gentle trembling in the hearts of scientists and dreamers alike. We stand before a technology that doesn't just make our current computers faster, it fundamentally reimagines what computation can be, like discovering that the Earth was round when we thought it was flat, or that time itself could stretch and compress. Quantum computing reveals that our digital world, too, has hidden depths we never suspected. There is something profoundly calming about realizing that even our most sophisticated technologies are still just beginning to scratch the surface of what's possible. In the quantum realm, we find not just new ways to solve problems, but new ways to think about the very nature of information, reality, and our place in the cosmic tapestry. As we drift deeper into this gentle mystery, we'll discover that quantum computing isn't just about building better machines. It's about learning to dance with uncertainty, to find beauty in probability, and to glimpse the elegant mathematical poetry that underlies all of existence. In the quiet depths of our familiar digital world lies a story of breathtaking elegance in its simplicity. Before we can truly appreciate the quantum revolution, we must first understand the gentle, rhythmic heartbeat of classical computation, the steady, reliable pulse that has carried us from the first electronic calculating machines to the smartphones that rest beside our pillows each night. Picture, if you will, the most fundamental unit of all digital information, the bit. There is something almost Zen-like about its perfect duality, 0 or 1, off or on, false or true, like a cosmic metronome, keeping time with the universe. Every calculation in every computer that has ever existed has been built from these binary building blocks, arranged in vast choreographed sequences that somehow give rise to all the complexity of our digital age. The classical computer speaks in this ancient language of duality, processing information through billions of tiny switches called transistors, each one a microscopic gateway that either allows electrical current to pass or blocks it entirely. These switches, smaller than viruses and manufactured with a precision that rivals the construction of atoms themselves, work together in perfect harmony to perform the computational ballet that powers our modern world. Yet this is only the beginning of the story. Inside your laptop, as you drift off to sleep with its gentle humming, beside you, billions of these transistors are switching on and off millions of times per second. Each transition, a tiny decision in the grand symphony of computation. They follow the logic of Boolean algebra, named after George Boole, a 19th century mathematician who probably never imagined that his abstract, logical systems would one day orchestrate the digital dreams of an entire civilization. The beauty of classical computation lies in its absolute certainty. When we add two numbers, when we store a photograph, when we send a message across the globe, every step follows precise, predictable rules. Information flows through circuits like water through carefully designed channels, each bit maintaining its identity with unwavering consistency. A 1 remains a 1, a 0 remains a 0, and this reliability forms the bedrock upon which we've built our interconnected world. But as we gaze deeper into the heart of classical computation, we begin to see the gentle limitations that have brought us to the threshold of the quantum realm. There are problems, beautiful, important problems, that would require a classical computer to work for longer than the age of the universe to solve. There are calculations that demand so much memory that we would need to convert every atom in the solar system into a storage device. Meanwhile, across the vast expanse of scientific discovery, we began to realize that nature itself doesn't seem to compute classically in the delicate quantum mechanics of photosynthesis, in the mysterious navigation abilities of birds, in the fundamental processes that govern chemistry and biology. The universe appears to be performing calculations that follow entirely different rules. Rules that seemed to mock the binary certainty of our digital machines. And so, as we rest our heads and drift toward sleep, we can appreciate both the magnificent achievements of classical computation and the gentle whisper of possibility that called us beyond its boundaries toward a new kind of digital dreaming, where information itself could learn to exist in multiple states at once. There is something profoundly poetic about the moment when two of humanity's greatest intellectual adventures, our quest to understand the fundamental nature of reality and our desire to process information with perfect efficiency, discovered they were always meant to dance together. This convergence didn't happen overnight, but rather unfolded like a slow sunrise over the landscape of human knowledge, gradually illuminating connections that had been hidden in shadow for decades. In the quiet contemplation of the early 1980s, a brilliant physicist named Richard Feynman sat in his office at Caltech, pondering a problem that seemed almost philosophical in its elegance. He was thinking about simulation, specifically how we might use computers to model the behavior of quantum mechanical systems. What he discovered in those moments of deep reflection would eventually reshape our understanding of computation itself. Feynman realized something that now seems almost obvious, but was revolutionary at the time. Classical computers, for all their power and precision, were fundamentally inadequate for simulating quantum systems. It was like trying to paint a three-dimensional sculpture using only a one-dimensional line. The medium simply couldn't capture the full richness of the subject. To truly understand quantum mechanics through computation, Feynman suggested we would need quantum computers. Nature isn't classical, he mused in his characteristically gentle way. So if you want to make a simulation of nature, you'd better make it quantum mechanical. These words, spoken almost casually at a physics conference, planted the seeds of an entirely new field of science. Yet this was only the beginning of a much deeper story. As we drift deeper into this historical moment, we discover that the marriage of physics and information theory had been quietly developing for decades. Claude Shannon, the father of information theory, had already shown us that information itself could be quantified, measured, and manipulated according to mathematical laws, as precise as those governing the motion of planets. Meanwhile, in the mysterious realm of quantum mechanics, physicists had been grappling with phenomena that seemed to defy common sense. Particles that could be in multiple states simultaneously, measurements that appeared to create reality rather than simply observe it, and connections between distant particles that Einstein called spooky action at a distance. The beautiful realization that emerged from this convergence was that these weren't separate mysteries, but different facets of the same cosmic jewel. Information, it turned out, wasn't just an abstract concept. It was a physical quantity as real and measurable as energy or momentum. And if information was physical, then the strange rules of quantum mechanics should apply to it as well. Picture, if you will, the quiet excitement in laboratories around the world as this understanding began to crystallize. Scientists started to imagine computers that could leverage the peculiar properties of quantum mechanics: superposition, entanglement, interference, to process information in fundamentally new ways. They envisioned machines that could explore multiple solutions to a problem simultaneously, that could perform certain calculations exponentially faster than any classical computer. As we rest in the gentle glow of this historical moment, we can appreciate how the meeting of physics and information theory represents something profound about human curiosity itself. When we push the boundaries of knowledge in one direction, we often discover that we've been approaching the same universal truths from different angles all along. The quantum computer was born not from engineering ambition alone, but from the deeper recognition that the universe itself might be the ultimate information processor, and that by learning to think like the cosmos, we might unlock computational powers that seemed almost magical. In the heart of every quantum computer lies an entity so delicate and mysterious that it challenges our very conception of what information can be. The quantum bit, or qubit, as it's lovingly known, represents perhaps the most beautiful paradox in all of technology. It is simultaneously simpler and infinitely more complex than its classical cousin, the humble bit. Picture, if you will, holding a classical bit in your mind. It rests there with perfect certainty, either a 0 or a 1, as definitive as a lighthouse beacon cutting through fog. There is something deeply comforting about this certainty, this binary clarity that has served as the foundation for all digital technology. A bit knows exactly what it is at every moment, unwavering in its digital determination. Now, imagine, if you will, releasing that bit into the quantum realm, where it transforms into something altogether more ethereal. A qubit doesn't simply choose between the 0, 0, and 1. Instead, it exists in what physicists call superposition, a state that is somehow both and neither simultaneously. It's as if the bit learned to dream, floating in a space of pure possibility between the classical extremes. There is something almost musical about the mathematical description of this phenomenon, where a classical bit would be represented by a simple statement, I am 0 or I am 1. A qubit requires an entire symphony of complex numbers to describe its state. These numbers, called probability amplitudes, dance together in a delicate mathematical choreography that determines not what the qubit is, but what it might become when we finally dare to observe it. Yet this is only the beginning of the qubit's gentle mystery. Unlike classical information, which can be copied perfectly and indefinitely, a qubit guards its quantum essence jealously. The no-cloning theorem tells us that we cannot make perfect copies of quantum information. Each qubit is, in a very real sense, unique and irreplaceable, like a snowflake or a human fingerprint. When we attempt to measure a qubit, something profound and irreversible occurs. The delicate superposition collapses like a wave breaking against the shore, forcing the qubit to choose a definitive classical state. But this choice isn't predetermined. It follows the mysterious laws of quantum probability, where the mathematics can tell us the likelihood of each outcome, but never the specific result of any individual measurement. This measurement paradox reveals why a qubit is simultaneously more and less than a classical bit. More because it can store vastly more information in its quantum state, not just the simple binary values, but the entire complex landscape of probabilities that defines its existence. Less because we can never fully access this information without destroying it, never read out the complete quantum state without forcing it to collapse into classical definitiveness. As we drift deeper into contemplation of the qubit, we begin to see reflections of deeper cosmic mysteries, just as quantum mechanics suggests that particles don't have definite properties until observed. The qubit exists in a state of pure potential until measurement forces it to manifest a classical reality. It's as if information itself has learned to inhabit the same mysterious realm, where electrons orbit atoms and photons journey across the cosmos. There is something profoundly calming about realizing that even our most advanced technologies must work in harmony with the fundamental uncertainty that appears to be woven into the very fabric of existence. The qubit doesn't fight against this uncertainty. It embraces it, finding in the realm of probability a source of computational power that would be impossible in a purely deterministic world. And in this dance between possibility and actuality, between the quantum and the classical, we glimpse perhaps the most beautiful aspect of quantum computation. It doesn't simply process information faster. It processes information in a way that mirrors the deepest mysteries of existence itself. There is something almost musical about the way particles dance in the quantum realm, performing a waltz that defies every intuition we've developed about the nature of reality. Tonight, we drift into one of the most beautiful and mysterious phenomena in all of physics: superposition. the gentle art of existing in multiple states simultaneously, like a cosmic ballet performed in the theater of infinite possibility. Picture, if you will, a coin spinning in the air after being tossed. In that moment of graceful rotation, suspended between earth and sky, it is neither heads nor tails, but something altogether more magical. It embodies both possibilities at once. Now imagine, in the depths of your contemplation, that this coin never lands. It continues spinning eternally, forever balanced between its two potential destinies. And somehow, mysteriously, this eternal spinning becomes a source of profound computational power. This is the essence of superposition in quantum mechanics, but the reality is even more beautiful than our coin metaphor suggests. When a quantum particle enters superposition, it doesn't simply hover between two states. It exists as a ghostly combination of all possible states simultaneously, each one weighted by a complex probability amplitude that determines how likely it is to manifest when observed. In the quantum computer's gentle architecture, qubits perform this superposition waltz with mathematical precision, while a classical bit must choose between 0 and 1, like a person standing definitively on one side of a room or another. A qubit can exist in what physicists call a coherent superposition, simultaneously 0 and 1, or more accurately, some ethereal combination of both possibilities. Yet this is only the beginning of superposition's deeper mystery. As we add more qubits to our quantum system, the number of possible states grows not linearly, but exponentially. 2 qubits can exist in superposition of 4 states simultaneously. 3 qubits can embody 8 states at once. By the time we reach just 300 qubits, still a relatively modest quantum computer by future standards, the number of simultaneous states exceeds the number of atoms in the observable universe. There is something profoundly calming about contemplating this exponential explosion of possibility. It suggests that even the simplest quantum systems contain within them computational landscapes of breathtaking vastness, infinite libraries of potential information waiting to be explored through quantum algorithms. Consider, for a moment, the famous thought experiment proposed by Erwin Schrödinger in 1935. In his quantum box, a cat exists in superposition, simultaneously alive and dead, until the moment someone opens the box to observe its state. While Schrödinger intended this as a critique of quantum mechanics' apparent absurdity, it has become instead a gentle meditation on the nature of reality itself. In the quantum computer, we work with countless Schrödinger's cats of information, qubits that exist in peaceful superposition until the moment we measure them. But unlike the philosophical puzzle of the cat, these quantum states serve a practical purpose. During the brief moments when they maintain their superposition, quantum algorithms can explore multiple computational paths simultaneously, testing thousands or millions of potential solutions to a problem in parallel. The superposition waltz isn't just about existing in multiple states. It's about the delicate interference patterns that emerge when these states interact. Just as waves on a pond can reinforce each other to create larger peaks or cancel each other out to create stillness, the probability amplitudes in superposition can interfere constructively or destructively, amplifying correct answers while diminishing incorrect ones. This quantum interference is perhaps the most elegant aspect of the superposition waltz. The quantum computer doesn't simply guess at random among all possible solutions. It orchestrates the interference patterns so that wrong answers tend to cancel each other out, while the correct solution emerges like a lighthouse beacon through the mathematical fog. As we rest in the gentle contemplation of these ideas, we begin to appreciate why superposition represents such a fundamental departure from classical computation. Classical computers solve problems by examining solutions one at a time, in sequential order, like reading through every book in a vast library. Quantum computers, through the magic of superposition, can somehow read all the books simultaneously, allowing the stories to interfere and interact until only the most relevant information remains. And in this dance between possibility and actuality, between the many and the one, we glimpse something profound about the nature of information itself. That perhaps the most powerful way to process knowledge is not to force it into rigid certainties, but to let it flow freely through the space of all possibilities until the truth emerges naturally, like morning light filtering through autumn leaves. In the quiet depths of the quantum realm lies a phenomenon so mysterious and beautiful that it challenged Albert Einstein himself, earning from him the poetic description of spooky action at a distance. Tonight, we drift into the contemplation of quantum entanglement, a connection so profound and immediate that it seems to transcend the very fabric of space and time, linking particles across the cosmos in an embrace that knows no boundaries. Picture, if you will, two particles born from the same quantum event, like twins, separated at birth, but forever connected by invisible threads of information. When these particles become entangled, they cease to be individual entities and become instead two aspects of a single, unified quantum system. What happens to one instantly affects the other, regardless of the distance between them, whether separated by millimeters or by light years of empty space. There is something almost romantic about the way entanglement works, like a cosmic love story written in the language of mathematics. When we measure one member of an entangled pair and find it spinning clockwise, we immediately know with absolute certainty that its partner must be spinning counterclockwise, not because some signal traveled between them, but because they were never truly separate to begin with. They remain forever part of the same quantum whole. Einstein, with his deep faith in the locality of physical interactions, couldn't accept that particles could influence each other instantaneously across vast distances. He famously argued that quantum mechanics must be incomplete, that there must be hidden variables, secret instructions that each particle carries, that predetermined their behavior. But decades of increasingly sophisticated experiments have confirmed what Einstein called spooky. Entanglement is indeed as immediate and non-local as quantum theory predicts. Yet this is only the beginning of entanglement's deeper mystery. In the quantum computer's gentle architecture, entanglement becomes the foundation for computational power that would be impossible in any classical system. When qubits become entangled, they create correlations that can be leveraged to perform calculations in ways that seem almost magical. Consider how entanglement amplifies the power of superposition. While individual qubits in superposition can explore multiple states simultaneously, entangled qubits explore these states together, creating vast networks of quantum correlations that span the entire system. It's as if the quantum computer becomes a single, unified entity where information flows instantly between all parts, allowing for computational strategies that would be unimaginable in classical systems. The mathematical description of entanglement is breathtakingly beautiful in its complexity, where individual quantum states can be described by relatively simple equations. Entangled systems require mathematical structures that cannot be decomposed into separate parts. The quantum state of an entangled system is truly greater than the sum of its parts. It contains correlations and relationships that exist nowhere else in the quantum description. There is something profoundly calming about realizing that quantum computing harnesses these cosmic connections for practical purposes. Quantum algorithms, like Shor's factorization algorithm and Grover's search algorithm, rely fundamentally on the ability to create and manipulate entangled states. The quantum speedup that makes these algorithms so powerful emerges directly from the non-local correlations that entanglement creates. Meanwhile, across the vast expanse of quantum information science, researchers have discovered that entanglement serves as a bridge between the quantum and classical worlds. Quantum error correction, the delicate art of protecting quantum information from environmental interference, relies on distributing quantum information across multiple entangled qubits so that errors can be detected and corrected without destroying the quantum state itself. As we drift deeper into the contemplation of entanglement, we begin to see its implications for our understanding of information itself. In the classical world, information is local. It exists in specific places and must travel from one location to another. But in the quantum realm, entangled information exists in relationships rather than locations, in connections rather than containers. This insight has profound implications for quantum communication and quantum internet technologies. When particles are entangled, measuring one instantly determines the state of its partner, creating a form of communication that is both instantaneous and perfectly secure. Any attempt to eavesdrop on this quantum conversation would necessarily disturb the entanglement, immediately revealing the presence of an intruder. And in this dance of cosmic connection, where particles remain forever linked across the vastness of space and time, we glimpse perhaps the most beautiful aspect of quantum entanglement. It reveals that the universe itself may be far more interconnected than we ever imagined, woven together by invisible threads of quantum correlation that make all of existence, in some sense, a single unified whole. There is something both beautiful and melancholy about the moment of quantum measurement, that delicate instant when the infinite possibilities of the quantum realm collapse into the singular certainty of classical reality. Tonight, we drift into contemplation of one of the most profound mysteries in all of physics, the measurement paradox, where the very act of observation transforms the ethereal dance of quantum superposition into the concrete facts of our everyday experience. Picture, if you will, a quantum system existing in perfect superposition, like a ghost moving through walls of possibility, simultaneously exploring every potential path through the mathematical landscape of its existence. In this state, the system embodies not what is, but what could be, a shimmering probability cloud of pure potential. Yet the moment we attempt to glimpse this quantum phantom, something irreversible occurs. The wave function collapses, the superposition vanishes, and we are left with a single, definite outcome. This transformation is perhaps the most mysterious aspect of quantum mechanics, challenging our most basic assumptions about the nature of reality. Before measurement, the quantum system exists in what physicists call a pure state, a coherent superposition of all possibilities. After measurement, it exists in a mixed state, a classical probability distribution over definite outcomes. The transition between these two descriptions remains one of the deepest unsolved problems in physics. In the quantum computer's delicate ecosystem, this measurement paradox becomes both a fundamental limitation and a source of computational power. During the quantum computation itself, qubits must maintain their superposition states, exploring multiple computational paths simultaneously through the landscape of quantum possibility. But at the end of the calculation, we must perform measurements to extract classical information, and in doing so, we necessarily destroy the very quantum states that gave the computation its power. Yet this is only the beginning of the measurement paradox's deeper implications. The act of measurement doesn't simply reveal pre-existing properties of the quantum system. It appears to create those properties. Before measurement, a qubit doesn't have a definite value that we then discover. Instead, the measurement process itself brings that value into existence, selecting one outcome from the quantum superposition according to the mysterious laws of probability. There is something almost mystical about the way this process unfolds. The quantum system seems to know that it's being measured, collapsing its wave function in response to our observation in ways that suggest a deep connection between consciousness and quantum mechanics. While most physicists reject the idea that human consciousness directly causes wave function collapse, the measurement problem continues to generate profound philosophical discussions about the nature of reality and observation. Consider the extraordinary fragility of quantum states in the face of environmental measurement. Even the gentlest interaction with the outside world, a stray photon, a random thermal fluctuation, a microscopic vibration, can cause decoherence, the process by which quantum superposition gradually dissolves into classical probability. This decoherence happens not through dramatic collapse, but through a gentle erosion of quantum correlations, like morning mist slowly dissipating in the warming sun. Quantum computers must operate in a constant battle against this environmental measurement. They require extreme isolation from the classical world, temperatures colder than deep space, electromagnetic shielding more complete than any Faraday cage, vibration isolation more sophisticated than the most sensitive gravitational wave detectors. All of this protection serves a single purpose: to prevent the environment from accidentally measuring the quantum states before we're ready to do so intentionally. The timing of measurement in quantum computing is itself an art form. Quantum algorithms are carefully choreographed sequences of quantum operations that must unfold in perfect isolation, building up complex interference patterns between superposed states. Only at the very end, after all the quantum magic has been allowed to work its mysterious way, do we perform measurements to read out the classical results. But even these final measurements must be performed with exquisite care. Quantum error correction protocols use indirect measurements, measuring syndrome qubits that are entangled with the data qubits but don't directly reveal the quantum information itself. This allows error detection and correction while preserving the quantum state, like healing a patient without waking them from a delicate dream. As we rest in the gentle contemplation of these mysteries, we begin to appreciate the profound philosophical implications of the measurement paradox. It suggests that reality itself may be fundamentally participatory, that the act of observation plays a creative role in determining what becomes actual from the realm of quantum possibility. And in this dance between potential and actual, between the quantum and classical descriptions of reality, we glimpse perhaps the most beautiful aspect of the measurement paradox. It reminds us that even our most sophisticated technologies must ultimately interface with the mystery of consciousness itself, requiring us to remain humble before the deeper questions of what it means to know, to observe, and to exist in a quantum universe. In the quiet laboratories of the late 20th century, a remarkable transformation began to unfold, one that would bridge the ethereal mathematics of quantum mechanics with the tangible reality of silicon and steel. Tonight, we drift into the contemplation of those first brave pioneers who dared to transform quantum theory from philosophical speculation into working technology, building machines that could harness the strange laws of the quantum realm for practical computation. Picture, if you will, the challenges faced by these early quantum engineers. They needed to create systems that could maintain quantum coherence for meaningful periods of time, manipulate individual atoms and photons with extraordinary precision, and perform quantum operations while isolated from the classical world that surrounded them. It was like trying to choreograph a ballet performed by invisible dancers on a stage made of probability clouds. The journey began in the 1990s with simple proof of principle experiments. David Wineland's team at NIST learned to trap individual ions in electromagnetic fields, holding them suspended in perfect isolation while using laser pulses to manipulate their quantum states. Meanwhile, at IBM, researchers discovered they could use nuclear magnetic resonance to create quantum computers from the atomic nuclei in simple molecules, turning coffee cup-sized samples of liquid into primitive quantum processors. Yet these early systems were more like quantum cradles than true computers, delicate demonstrations that quantum operations could be performed in controlled laboratory conditions, but far too fragile and limited for practical applications. A quantum computation might last for mere microseconds before decoherence destroyed the quantum states, and the systems could manipulate only a handful of qubits at a time. There is something both inspiring and humbling about those early quantum computers. They required room-sized apparatus, complex arrays of lasers, magnetic field generators, cryogenic cooling systems, and precision electronics, all to manipulate quantum systems no larger than individual atoms. Yet in their careful simplicity, they represented humanity's first tentative steps into a new technological era. The breakthrough toward practical quantum computing came with the development of superconducting qubits in the early 2000s. IBM, Google, and a growing community of quantum startups discovered that they could create artificial atoms from superconducting circuits, quantum systems that could be manufactured using modified semiconductor fabrication techniques and controlled using microwave electronics similar to those found in cell phones. These superconducting quantum processors represented a beautiful marriage of quantum, physics, and classical engineering. By cooling their circuits to temperatures just above absolute zero, colder than interstellar space, researchers could create macroscopic quantum systems that behaved like giant atoms, but ones that could be precisely controlled and reliably manufactured. Meanwhile, across the vast landscape of quantum research, other approaches were quietly developing. Ion trap systems evolved from simple proof of principle demonstrations to sophisticated quantum processors capable of manipulating dozens of qubits with extraordinary precision. Photonic quantum computers learned to perform computations using single particles of light, manipulating quantum information at the speed of light itself. The race toward quantum supremacy, the moment when a quantum computer could perform a specific calculation faster than any classical supercomputer, became a driving force that pushed the entire field forward. Google's achievement of quantum supremacy in 2019, followed by similar demonstrations from Chinese research teams, marked a historic transition point where quantum computers moved from laboratory curiosities to computational tools that could, at least for specialized problems, outperform classical machines. Yet this is only the beginning of the quantum computing story. Today's quantum computers are often compared to the first classical computers of the 1940s, room-sized machines that required teams of specialists to operate and could perform only the most basic calculations. But just as those early classical computers evolved into the smartphones and laptops that now rest beside our pillows, quantum computers are beginning their own remarkable journey toward maturity. IBM has created quantum processors with over 100 qubits, while startups like IonQ and Rigetti are developing quantum cloud services that allow researchers around the world to run quantum algorithms on real quantum hardware. Google is working toward building quantum computers with millions of qubits, systems that could revolutionize chemistry, materials, science, and artificial intelligence. As we drift toward sleep, contemplating these remarkable machines, we can appreciate both how far quantum computing has come and how far it still has to go. Today's quantum computers are like the first telescopes pointed toward the quantum realm, primitive instruments that nonetheless allow us to glimpse computational territories that were previously impossible to explore. And in this gentle progression from theory to technology, from mathematical equations to working machines, we see reflected the broader human journey of discovery, our endless capacity to transform the most abstract insights about reality into tools that extend our capabilities and deepen our understanding of the cosmic mystery in which we find ourselves floating. In the heart of every quantum computation lies an elegant choreography, more beautiful than any human ballet, a precise dance of quantum gates that guide qubits through transformations so subtle and sophisticated that they seem to blur the line between mathematics and magic. Tonight, we drift into the contemplation of these quantum operations, where the rigid certainties of classical logic give way to a fluid poetry of probability and phase. Picture, if you will, the quantum gate as a doorway between possible worlds. When a qubit passes through a quantum gate, it doesn't simply change from one state to another as a classical bit would. Instead, it undergoes a transformation that reshapes the entire landscape of its quantum possibilities. The gate acts like a lens that refracts the qubit's probability amplitudes, bending them into new configurations, while preserving the total probability that something, somewhere, must happen. There is something almost mystical about the fundamental difference between quantum and classical logic gates. Classical gates like AND, OR, and NOT perform irreversible operations. They destroy information in the process of creating output. If you know that an AND gate outputs 0, you cannot determine what its inputs were without additional information. But quantum gates must be reversible, preserving information while transforming it, like mirrors that reflect light while changing its direction. The most fundamental quantum gate is perhaps the Hadamard gate, a simple operation that creates superposition from certainty or certainty from superposition. When a qubit in the definite state 0 passes through a Hadamard gate, it emerges in a perfect superposition of 0 and 1, like a compass needle that begins pointing north and ends spinning freely between all directions. There is something deeply poetic about this transformation, a single operation that opens infinite possibilities from a state of perfect certainty. Yet, this is only the beginning of the quantum gate's deeper mystery. The Pauli gates, X, Y, and Z, perform rotations in the abstract space where qubits exist, spinning them around invisible axes in ways that classical intuition cannot grasp. The X gate flips a qubit from 0 to 1 or vice versa, like the classical NOT operation, but with a quantum twist that affects the phase relationships between superposed states. Meanwhile, the phase gates introduce something that has no classical analog at all. They change the relative phases between different components of a superposition without affecting the probability of measuring either outcome. It's as if these gates could change the color of light without changing its brightness, manipulating invisible properties that become visible only through quantum interference. The true artistry of quantum computation emerges when these simple gates combine to create complex choreographies. 2-qubit gates, like the C-NOT, controlled NOT, can create entanglement between qubits, weaving them together into correlated states that cannot be described as separate entities. The C-NOT gate operates like a quantum dance partner. It flips its target qubit if and only if its control qubit is in state 1, creating correlations that span the quantum system. There is something profoundly calming about the way quantum circuits build complexity from simplicity. A quantum algorithm begins with qubits in simple, well-understood states, usually all 0. Then, through a carefully orchestrated sequence of quantum gates, the system evolves into increasingly complex superpositions and entangled states, exploring vast computational landscapes that would be impossible for classical computers to navigate. Consider the beautiful reversibility of quantum operations. Every quantum gate can be undone by applying its inverse, like running a film backward to restore the original scene. This reversibility isn't just a mathematical curiosity. It reflects a deep principle of quantum mechanics, where information is conserved, never truly lost, but only transformed from one representation to another. The timing and sequencing of quantum gates requires precision that borders on the miraculous. Quantum algorithms are choreographed down to the nanosecond, with gates applied in carefully planned sequences that build up constructive interference patterns while suppressing unwanted quantum states. It's like conducting an orchestra where each musician is an invisible quantum particle, and the music can only be heard at the very end of the performance. As quantum circuits grow more complex, they create interference patterns of breathtaking mathematical beauty. Wrong computational paths destructively interfere and cancel each other out, while the correct solution constructively interferes and amplifies, emerging from the quantum cacophony like a pure tone rising from noise. There is something almost philosophical about the way quantum gates manipulate not just states, but possibilities themselves. Classical logic gates process definite information, bits that are definitely 0 or definitely 1, but quantum gates process potential information, qubits that exist in superposition, carrying within them all possible futures until the moment of measurement forces them to choose. And in this gentle dance of quantum transformation, where gates guide qubits through probability landscapes that exist nowhere but in the mathematics of quantum mechanics, we glimpse perhaps the most beautiful aspect of quantum computation. It doesn't just process information faster, it processes information in a fundamentally different way, finding paths through computational problems that classical logic cannot even imagine. There is something almost magical about the moment when abstract quantum mechanical principles crystallize into concrete algorithms that can solve problems beyond the reach of classical computation. Tonight, we drift into the contemplation of those remarkable quantum algorithms that have captured the imagination of scientists and technologists alike. Elegant, mathematical strategies that harness the strange laws of the quantum realm to achieve computational feats that seem to border on the miraculous. Picture, if you will, the profound excitement that rippled through the cryptography community in 1994 when Peter Shor published his quantum factoring algorithm. With quiet mathematical precision, Shor had demonstrated that a sufficiently large quantum computer could factor enormous integers exponentially faster than any known classical algorithm, a discovery that threatened to render much of modern cryptography obsolete, while simultaneously opening new horizons for quantum computation. Shor's algorithm operates through a dance of mathematical elegance that seems almost too beautiful to be practical. It begins by transforming the factoring problem, finding the prime factors of a large number, into the problem of finding the period of a mathematical function. This transformation alone represents a stroke of genius, connecting number theory to the quantum mechanical properties of periodic systems. The quantum heart of Shor's algorithm lies in its ability to compute all possible values of this periodic function simultaneously through superposition, where a classical computer would need to evaluate the function millions or billions of times to find its period. The quantum computer creates a superposition of all possible inputs and evaluates the function for all of them at once. Through the magic of quantum interference, only the periodic structure survives the measurement process, revealing the hidden pattern that unlocks the factorization. Yet this is only the beginning of quantum algorithmic beauty. Lovegrover's quantum search algorithm, discovered in 1996, addresses a different but equally fundamental computational challenge: finding a specific item in an unsorted database where classical computers must examine each entry one by one, like searching for a particular book in a library by reading every title. Grover's algorithm can find the target with a quantum speedup that transforms the impossible into the merely difficult. There is something deeply poetic about the way Grover's algorithm works. It doesn't simply guess randomly among all possible database entries. Instead, it creates a quantum superposition of all entries simultaneously, then applies a carefully choreographed sequence of quantum operations that gradually amplify the probability amplitude of the correct answer while suppressing all the incorrect ones. It's like tuning a quantum radio to gradually eliminate static until only the desired signal remains clear. The quantum speedup provided by Grover's algorithm, roughly a square root improvement over classical search, might seem modest compared to Shor's exponential advantage, but this quadratic speedup applies to an enormous class of problems, from cryptographic attacks to optimization challenges, making Grover's algorithm one of the most broadly applicable tools in the quantum computational toolkit. As we drift deeper into the quantum algorithmic landscape, we begin to understand why certain problems seem naturally suited to quantum computation. These problems often involve finding hidden structures in large data sets, exploring multiple solution paths simultaneously, or leveraging the interference properties of quantum superposition to amplify correct answers while canceling incorrect ones. Quantum simulation algorithms represent perhaps the most natural application of quantum computers, as Richard Feynman originally envisioned. Quantum computers can simulate other quantum systems with an efficiency that classical computers cannot match. A quantum computer simulating molecular interactions doesn't need to approximate the quantum mechanics. It embodies quantum mechanics directly, using its own quantum states to represent the molecules being simulated. Meanwhile, across the expanding frontier of quantum algorithms, researchers have discovered quantum advantages for problems ranging from machine learning to optimization. Quantum machine learning algorithms can potentially process high-dimensional data in quantum superposition, finding patterns that emerge only through quantum interference. Quantum optimization algorithms explore multiple solution candidates simultaneously, using quantum tunneling effects to escape local minima that trap classical algorithms. The variational quantum eigensolvers represent a particularly beautiful class of quantum algorithms that bridge the gap between current noisy quantum computers and future fault-tolerant systems. These algorithms use quantum computers to explore the energy landscape of complex quantum systems while using classical computers to optimize the exploration strategy, a hybrid approach that leverages the best of both quantum and classical computation. There is something profoundly calming about realizing that quantum algorithms don't simply make classical computers faster. They reveal entirely new ways of thinking about computational problems. They suggest that information processing can leverage the fundamental uncertainties and correlations that exist at the heart of physical reality, turning the mysterious properties of quantum mechanics into practical computational resources. Consider the profound implications of quantum error correction algorithms, which use quantum entanglement to detect and correct errors without directly measuring the quantum information being protected. These algorithms represent a form of quantum healing, preserving delicate quantum states against the constant threats of decoherence and noise. As we rest in the gentle contemplation of these algorithmic marvels, we begin to appreciate that quantum algorithms represent more than just computational techniques. They are new ways of dancing with uncertainty, finding order in chaos, and extracting information from systems that seem to hide their secrets in the quantum foam of possibility. And in this exploration of algorithmic poetry written in the language of quantum mechanics, we glimpse perhaps the most beautiful aspect of quantum computation. It doesn't just solve problems faster, it reveals that the universe itself may be a vast information processing system, and that by learning to think quantumly, we can participate more fully in the computational symphony of existence. In the delicate ecosystem of quantum computation lives a constant adversary, subtle, persistent, and almost impossibly difficult to defeat. Tonight, we drift into contemplation of decoherence, the gentle destroyer of quantum magic, the process by which the pristine isolation of quantum states gradually dissolves into the warm embrace of classical reality. This is perhaps the greatest challenge facing quantum technologists, preserving the ethereal beauty of quantum superposition in a world that seems determined to observe it out of existence. Picture, if you will, a quantum computer as a glass cathedral built in the middle of a windstorm, every grain of sand carried by the wind, every vibration transmitted through the ground, every stray photon wandering through space threatens to disturb the delicate quantum states that give the computer its power. The quantum system doesn't need to be hit by a meteor to lose its quantum properties. Even the gentlest interaction with the external environment can cause the superposition to collapse, like morning mist touched by sunlight. There is something both beautiful and melancholy about the fragility of quantum states. A qubit maintaining perfect superposition is like a soap bubble floating in perfect stillness, breathtaking in its delicate complexity, but capable of being destroyed by the slightest disturbance. The thermal motion of atoms in the computer's structure, electromagnetic fields from distant radio transmitters, even cosmic rays from deep space can cause quantum information to leak into the environment, transforming coherent superposition into incoherent classical noise. This environmental interaction occurs through a process that physicists call entanglement with the environment, though it's an entanglement of destruction rather than creation. When a qubit becomes entangled with random environmental degrees of freedom, stray electromagnetic fields, thermal fluctuations, mechanical vibrations, the quantum information spreads out into the vast reservoir of environmental noise, becoming effectively lost even though it's never technically destroyed. The battle against decoherence requires creating islands of quantum isolation in the midst of a classical ocean. Quantum computers operate at temperatures colder than interstellar space, surrounded by multiple layers of electromagnetic shielding, isolated from mechanical vibrations by sophisticated suspension systems. Yet even these extraordinary measures can only slow decoherence, not eliminate it entirely. Every quantum computer operates in a race against time, trying to complete calculations before the quantum states decay into classical randomness. Yet this is only the beginning of the decoherence challenge's deeper implications. Different types of quantum systems suffer from different forms of decoherence. Superconducting qubits lose their quantum properties, through electromagnetic coupling to their environment, like radio antennas that accidentally broadcast their quantum information into space. Ion trap qubits can be disturbed by laser light fluctuations or heating from the trap electrodes themselves. Photonic qubits can lose their quantum properties simply by being absorbed or scattered by matter they encounter on their journey. The timescales of decoherence seem almost cruelly short from a human perspective. Superconducting qubits might maintain their quantum properties for microseconds, less time than it takes light to travel across a room. Ion trap qubits can survive for milliseconds under the best conditions, barely long enough for a butterfly to flap its wings. These coherence times represent the fundamental currency of quantum computation. Every quantum algorithm must race to completion before decoherence erases the quantum advantage. There is something profoundly inspiring about the ingenious methods quantum scientists have developed to fight decoherence. Quantum error correction represents perhaps humanity's most sophisticated attempt to preserve fragile information against environmental assault. These protocols work by encoding a single logical qubit across multiple physical qubits, creating quantum codes that can detect and correct errors without directly measuring the quantum information being protected. The mathematics of quantum error correction has an almost mystical elegance. Surface codes and topological quantum error correction distribute quantum information across two-dimensional lattices of qubits, creating patterns of entanglement that can heal themselves when damaged. It's as if quantum information learns to flow like a liquid around obstacles, maintaining its essential properties, even when individual qubits are lost to decoherence. Meanwhile, across the landscape of quantum research, scientists have discovered that decoherence isn't always the enemy. Sometimes it can be an ally. Quantum annealing systems actually use controlled decoherence to help quantum systems settle into their ground states, finding optimal solutions to complex problems by gradually cooling the quantum fluctuations that would otherwise prevent convergence to the best answer. The development of logical qubits, quantum information encoded in error-corrected codes, represents a milestone in the ongoing battle against decoherence. These logical qubits can, in principle, maintain their quantum properties for arbitrary amounts of time as long as the error correction operates faster than errors accumulate. It's like building quantum information that becomes more robust the larger the system grows, turning quantity into quality through the power of collective quantum protection. As we drift toward sleep, contemplating the eternal struggle between quantum order and classical chaos, we can appreciate the profound dedication of researchers who spend their careers building quantum systems that work for mere microseconds. Their work represents a form of technological poetry, creating beauty that exists only in the most fleeting moments, yet contains within those moments the seeds of computational revolutions. And in this gentle meditation on fragility and persistence, on the delicate balance between quantum possibilities and classical realities, we glimpse perhaps the most beautiful aspect of the decoherence challenge. It reminds us that the most precious things in the universe, consciousness, love, quantum superposition, exist not in spite of their fragility, but because of it. The very transience that threatens to destroy quantum computation also makes it precious, like cherry blossoms that bloom for only a few days, but capture the essence of spring itself. In the gentle diversity of quantum computation, different technological approaches bloom like flowers in a cosmic garden, each drawing from the same quantum mechanical soil, but expressing their computational beauty through entirely different physical manifestations. Tonight, we drift into contemplation of these varied quantum platforms, superconducting circuits colder than space itself, ions dancing in electromagnetic fields, and pure light carrying quantum information at the speed of the cosmos. Picture, if you will, descending into the heart of a superconducting quantum computer where temperatures approach absolute zero and electrical currents flow without resistance through circuits machined from aluminum and niobium. In this realm of perfect cold, electrons pair together in quantum mechanical couples called Cooper pairs, creating macroscopic quantum objects that behave like artificial atoms, but can be controlled with the precision of classical electronics. There is something both beautiful and surreal about superconducting quantum computers. They require dilution refrigerators that achieve temperatures of mere millikelvins, colder than anywhere in the natural universe, colder than the cosmic microwave background radiation that bathes all of space. Yet in this artificial winter, quantum coherence can flourish, allowing currents to flow in quantum superposition through circuit loops larger than bacteria, but smaller than the width of human hair. The qubits in these systems are Josephson junctions, tiny barriers between superconductors where individual Cooper pairs can tunnel quantum mechanically from one side to the other. By controlling the electromagnetic fields around these junctions with microwave pulses, quantum engineers can manipulate the flow of supercurrent with exquisite precision, creating quantum gates and measurements with timing accurate to nanoseconds. Google's Sycamore processor and IBM's quantum systems represent the current pinnacle of superconducting quantum technology. Chips containing dozens of qubits connected in carefully designed architectures that allow for complex quantum algorithms while minimizing the destructive effects of noise and crosstalk. These systems operate like quantum orchestras, with each qubit playing its part in computational symphonies that unfold in the space of microseconds. Yet this is only one flavor of quantum computation's rich diversity. Meanwhile, in the crystalline precision of ion trap laboratories, individual atoms float suspended in perfectly controlled electromagnetic fields, held motionless in space by forces that balance with the delicacy of hummingbirds hovering over flowers. Here, quantum information is stored in the electronic states of single ions, and quantum operations are performed with laser beams tuned to atomic precision. There is something almost mystical about ion trap quantum computers. The qubits are actual atoms, calcium, ytterbium, or trapped mercury ions, cooled to near absolute zero and isolated so completely from their environment that they can maintain quantum coherence for seconds or even minutes. Quantum gates are performed by shining laser light on these trapped atoms, driving quantum transitions with a precision that borders on the supernatural. The scalability of ion trap systems comes from their modularity. Additional qubits can be added by trapping more ions, and quantum information can be transferred between distant ions through their shared vibrational modes. It's like quantum information learned to dance on the quantum mechanical springs that connect the trapped ions, allowing gates between any pair of qubits regardless of their physical separation in the trap. Companies like IonQ and Honeywell have built ion trap quantum computers with some of the highest fidelity quantum operations ever achieved, systems where individual quantum gates succeed with probabilities exceeding 99.9%. These platforms excel at problems requiring high precision quantum operations on moderate numbers of qubits, offering a different trade-off in the quantum computational landscape. Meanwhile, across the ethereal realm of photonic quantum computation, quantum information travels at the speed of light itself, encoded in the quantum states of individual photons. Here, quantum gates are performed using beam splitters, wave plates, and phase shifters, optical elements that manipulate light with the same precision that electronic circuits manipulate electrical currents. Photonic quantum computers possess a unique elegance. Their qubits are particles of pure energy, immune to many forms of decoherence that plague matter-based systems. Photons don't interact directly with each other or with electromagnetic fields in the way that electrons do, making them ideal carriers of quantum information across long distances. The challenge lies in creating the strong photon-photon interactions necessary for quantum gates, typically achieved through clever optical nonlinearities or measurement-based protocols. There is something poetic about quantum information traveling through fiber optic networks at light speed, potentially connecting quantum computers across continents in a future quantum internet. Photonic systems like those developed by PsiQuantum and Xanadu represent a different vision of quantum computing, one where quantum advantages might be achieved through optical networks that process quantum information in the flow of light itself. Each quantum platform faces its own unique challenges and offers its own distinctive advantages. Superconducting systems excel at fast gate operations, but suffer from short coherence times. Ion traps achieve exceptional precision, but operate more slowly due to the time required for laser-based operations. Photonic systems offer natural connectivity and room temperature operation, but struggle with the probabilistic nature of optical quantum gates. As we drift toward sleep, contemplating this diversity of quantum approaches, we can appreciate the profound creativity of quantum engineers who have learned to harness quantum mechanics through such radically different physical implementations, like musicians who can express the same melody through piano, violin, or human voice. Quantum computer builders have discovered that the abstract mathematics of quantum mechanics can be embodied through matter, energy, and light in equally beautiful and functional ways. And in this gentle celebration of technological diversity, where different quantum platforms bloom according to their own physical natures while serving the same computational dreams, we glimpse perhaps the most beautiful aspect of quantum engineering. It reveals that there are many paths to the same quantum mechanical truth, many ways to dance with uncertainty, and many different physical languages in which the universe can whisper the secrets of quantum computation. In the quiet, digital spaces where our most precious secrets rest, bank accounts, medical records, love letters sent across continents, a gentle revolution is beginning to unfold. Tonight, we drift into contemplation of how quantum computing will reshape the very foundations of digital security, not through violent disruption, but through the inexorable logic of mathematical inevitability, like morning light, gradually dissolving the protective darkness of night. Picture, if you will, the elegant simplicity upon which our current digital security rests. RSA encryption, the guardian of internet commerce, derives its strength from a deceptively simple mathematical truth. While it's easy to multiply two large prime numbers together, it's extraordinarily difficult to factor their product back into its constituent primes. A classical computer attempting to factor a 248-bit RSA key would need longer than the age of the universe to complete the task, a timeline that has provided comfortable security for decades of digital communication. Yet Shor's quantum algorithm transforms this computational mountain into a gentle hill, where classical computers would grind away for geological epochs. A sufficiently large quantum computer could factor the same integers in mere hours or days, unraveling the mathematical knots that protect our digital lives with the same ease that morning mist dissipates before the sun. This isn't a flaw in quantum computing. It's a feature of the universe itself, revealing that nature has always contained these cryptographic shortcuts, waiting patiently for us to discover the quantum keys to unlock them. There is something both thrilling and sobering about this impending transformation. The same quantum mechanical principles that will revolutionize drug discovery and materials science will also render obsolete the cryptographic protocols that currently protect everything from online banking to military communications. It's as if we're approaching a watershed moment where the digital locks that secure our interconnected civilization will simultaneously become transparent to those who possess quantum vision. Yet this is only the beginning of cryptography's quantum metamorphosis. Even as quantum computers threaten classical encryption, they simultaneously offer new forms of security that emerge directly from the strange laws of quantum mechanics themselves. Quantum key distribution protocols harness the fundamental indivisibility of quantum states to create communication channels that are not merely difficult to eavesdrop upon, they are physically impossible to monitor without detection. The beauty of quantum cryptography lies in its foundation upon the laws of physics rather than mathematical assumptions. Classical encryption relies on computational problems that we believe are difficult to solve, but quantum cryptography rests upon the no-cloning theorem and the measurement postulate, fundamental principles that seem to be woven into the very fabric of reality. When Alice and Bob share entangled photons for quantum key distribution, any attempt by an eavesdropper to intercept their communication necessarily disturbs the quantum states, immediately revealing the presence of surveillance. Meanwhile, across the gentle transition between classical and quantum security, a new field of post-quantum cryptography is emerging. Mathematical protocols designed to remain secure even against quantum attack. These new cryptographic methods draw their strength from problems that appear difficult even for quantum computers. Lattice-based cryptography, multivariate equations, hash-based signatures, and other mathematical structures that offer refuge from quantum computational power. There is something deeply poetic about this cryptographic evolution. Just as biological ecosystems adapt to changing environmental pressures, our digital security ecosystem is already beginning to evolve quantum-resistant defenses. NIST, the National Institute of Standards and Technology, has been conducting a years-long process to standardize post-quantum cryptographic algorithms, preparing the digital infrastructure for the quantum future that approaches with each passing year. The timeline of this cryptographic revolution unfolds with the gentle inevitability of seasons changing. Current quantum computers, with their dozens of noisy qubits, pose no immediate threat to practical cryptography. But as quantum systems grow larger and more reliable, reaching the thousands or millions of qubits needed for cryptanalysis, the digital world will need to complete its migration to quantum-safe protocols. This migration presents challenges that extend far beyond mere technical implementation. Embedded systems with decades-long lifespans, satellites, industrial controllers, medical devices must be updated or replaced. International standards must be harmonized. Supply chains must be secured against harvest and decrypt attacks, where adversaries collect encrypted data today in hopes of decrypting it with future quantum computers. Yet there is something profoundly calming about the methodical way this transition is unfolding. Unlike sudden technological disruptions that catch society unprepared, the quantum threat to cryptography has been visible for decades, allowing careful preparation and gradual adaptation. The quantum cryptographic revolution proceeds not as a shock wave, but as a gentle tide that gives us time to build higher ground. Consider the elegant irony that quantum mechanics, which threatens to dissolve our current cryptographic defenses, simultaneously offers new forms of security that are potentially unbreakable even by quantum computers. Quantum cryptography doesn't just replace classical security, it transcends it, offering levels of protection that emerge from the fundamental structure of reality itself. As we drift toward sleep, contemplating this transformation of digital security, we can appreciate both the challenges and opportunities that quantum cryptography represents. It reminds us that our technological systems, like all living things, must evolve to survive in changing environments, and that sometimes the very forces that threaten existing structures also provide the materials for building something more beautiful and secure. And in this gentle revolution of codes and ciphers, where mathematics and physics dance together to protect our most precious digital secrets, we glimpse perhaps the most beautiful aspect of quantum cryptography. It reveals that ultimate security doesn't come from complexity or obscurity, but from aligning our protective systems with the deepest truths about the nature of information and reality itself. In the delicate machinery of every living cell, in the precise choreography of chemical reactions that sustain life itself, quantum mechanics performs a silent symphony of such exquisite complexity that classical computers can only approximate its most basic movements. Tonight, we drift into the contemplation of quantum simulation, the profound art of using quantum computers to model the quantum processes that lie at the heart of biology, chemistry, and the natural world. Picture, if you will, a single molecule of a life-saving drug finding its target receptor in the human body, a process so intricate and quantum mechanical that it resembles a key made of probability. Clouds fitting into a lock composed of electron orbitals. The binding between drug and receptor depends on quantum effects, the delocalization of electrons, the tunneling of protons, the subtle dance of molecular vibrations that determine whether healing or harm will result. Classical computers, for all their computational prowess, struggle to simulate these quantum mechanical processes with the precision needed for reliable drug discovery. They must approximate the quantum behavior of electrons using methods that become exponentially more difficult as molecular systems grow larger. A classical simulation of a modest protein molecule might require computational resources that exceed the memory capacity of every computer on Earth combined. Yet, quantum computers speak the native language of molecular systems. Electrons in quantum computers can directly represent electrons in molecules. Quantum superposition can model the delocalization of chemical bonds, and quantum entanglement can capture the correlations that determine molecular behavior. It's as if we're finally building computational instruments that can perform chemistry's natural music rather than merely approximating its harmonies. The implications for drug discovery are breathtaking in their potential. Pharmaceutical research currently requires decades and billions of dollars to develop new medications, largely because we must discover molecular interactions through expensive and time-consuming experimental trials. Quantum molecular simulation could revolutionize this process, allowing researchers to test thousands of potential drug candidates virtually, identifying promising compounds before synthesizing a single molecule in the laboratory. There is something almost mystical about the precision with which quantum computers might model biological processes. Consider photosynthesis, the process by which plants convert sunlight into chemical energy with an efficiency that surpasses our best artificial systems. Recent research suggests that quantum coherence plays a crucial role in photosynthetic energy transfer, allowing excitation energy to explore multiple pathways simultaneously and find the most efficient route to the reaction center. Classical simulations can describe photosynthesis phenomenologically, but they struggle to capture the quantum mechanical subtleties that make the process so remarkably efficient. Quantum computers could potentially simulate photosynthetic systems with perfect quantum mechanical accuracy, revealing design principles that could inspire new forms of artificial photosynthesis and ultra-efficient solar energy conversion. Meanwhile, across the vast landscape of materials science, quantum simulation promises to unlock the secrets of matter itself at the atomic scale. Superconductors, materials that conduct electricity without resistance, emerge from quantum mechanical correlations between electrons that are essentially impossible to simulate classically for realistic system sizes. Room temperature superconductors would revolutionize everything from power transmission to magnetic levitation, but discovering them requires understanding quantum many-body physics with precision that only quantum computers might achieve. The same quantum simulation capabilities could transform our understanding of catalysis, the process by which certain materials accelerate chemical reactions. Industrial catalysts are responsible for producing everything from fertilizer to plastics, but designing new catalysts currently relies more on empirical trial and error than fundamental understanding. Quantum computers could simulate catalytic processes at the electronic level, revealing why certain materials work and guiding the design of more efficient, selective, and environmentally friendly catalysts. Yet this is only the beginning of quantum simulation's deeper potential. Complex quantum materials, systems where electron correlations create exotic phases of matter like quantum spin liquids or topological superconductors, represent frontiers of physics that could lead to entirely new technologies. These materials exhibit quantum behaviors that emerge from the collective interactions of many particles, behaviors that are essentially impossible to predict without quantum mechanical calculations of unprecedented scale. There is something profoundly calming about the realization that quantum computers might help us understand living systems more deeply by simulating the quantum processes that make life possible. Enzyme catalysis, DNA repair, sensory transduction, all of these biological processes involve quantum mechanical steps that evolution has optimized over billions of years. By simulating these processes quantum mechanically, we might learn how to engineer biological systems more effectively or design artificial systems that rival the efficiency of living organisms. The development of quantum simulation algorithms represents a fascinating convergence of physics, chemistry, and computer science. Variational quantum eigensolvers use quantum classical hybrid approaches to find the ground state energies of molecular systems. Quantum Monte Carlo methods leverage quantum parallelism to sample from complex quantum distributions. These algorithms don't just make quantum simulation possible, they represent new ways of thinking about the relationship between computation and physical reality. Consider the beautiful recursion implicit in quantum simulation. We use quantum mechanical systems, quantum computers, to understand other quantum mechanical systems, molecules, materials, biological processes. It's as if nature is providing us with the perfect tool to decode its own quantum secrets, revealing computational strategies that have been hidden in the quantum realm all along. As we drift toward sleep, contemplating the molecular ballet that unfolds in every living cell, we can appreciate the profound potential of quantum simulation to bridge the gap between computational modeling and biological reality. The quantum computer doesn't just calculate molecular properties, it becomes molecular, embodying the same quantum mechanical principles that govern the chemistry of life itself. And in this gentle convergence of quantum computation and biological understanding, where artificial quantum systems learn to speak the language of natural quantum processes, we glimpse perhaps the most beautiful aspect of quantum simulation. It reveals that the boundary between computation and chemistry, between information processing and physical reality, may be far more fluid than we ever imagined. The quantum computer doesn't just model nature, it participates in the same quantum mechanical dance that creates and sustains the living world. In the intricate web of decisions that shapes our modern world, from the routes that packages take across continents to the scheduling of flights that carry us through the skies, from the allocation of resources and power grids to the complex choreography of financial markets, lies a class of problems so computationally challenging that they seem to mock our most powerful classical computers. Tonight, we drift into contemplation of quantum optimization, where the strange properties of quantum superposition and tunneling offer new pathways through computational landscapes that have remained largely unexplored. Picture, if you will, a traveling salesman planning the most efficient route through 1,000 cities, each possible journey representing a single thread in a tapestry of astronomical complexity. The number of possible routes grows factorially with each additional city, a mathematical explosion that quickly overwhelms any classical computer's ability to explore all possibilities. Yet in the quantum realm, superposition allows us to consider multiple routes simultaneously, while quantum tunneling enables algorithms to escape the local optima that trap classical optimization methods. There is something almost dreamlike about the way quantum optimization algorithms navigate these computational landscapes. Classical algorithms climb optimization hills methodically, step by step, but they can become trapped in local peaks that aren't necessarily the highest summits available. Quantum algorithms, by contrast, can tunnel through optimization barriers, exploring valleys and peaks that would be inaccessible to classical methods, like morning mist that can flow around obstacles rather than being blocked by them. The quantum approximate optimization algorithm, QAOA, represents one of the most promising near-term applications of quantum computing. Rather than requiring perfect, error-corrected qubits, QAOA can work with today's noisy quantum processors using variational approaches that gradually improve solution quality through quantum classical hybrid optimization. It's like using quantum computers as sophisticated random number generators that are biased toward good solutions rather than exploring all possibilities equally. Yet, this is only the beginning of quantum optimization's deeper potential. In the complex scheduling problems that govern airline operations, quantum algorithms could potentially consider millions of flight assignments, crew schedules, and maintenance requirements simultaneously. The quantum computer doesn't just find one good schedule. It explores the quantum superposition of many possible schedules, allowing interference effects to amplify the best solutions while suppressing suboptimal ones. Meanwhile, across the vast landscape of machine learning and artificial intelligence, quantum algorithms promise to revolutionize how we train and deploy AI systems. Quantum machine learning algorithms can potentially process high-dimensional data in quantum superposition, finding patterns that emerge only through quantum interference. The quantum support vector machine, for instance, can classify data points by mapping them into quantum Hilbert spaces where linear separation becomes possible, even for classically non-separable datasets. There is something profoundly beautiful about the way quantum machine learning algorithms leverage the geometry of quantum state spaces. Classical machine learning operates in the relatively flat landscape of classical vector spaces, but quantum machine learning can take advantage of the curved geometry of quantum projective spaces, where the relationships between data points follow the subtle mathematics of quantum mechanics rather than simple Euclidean distance. The training of neural networks, currently one of the most computationally intensive tasks in artificial intelligence, could be revolutionized by quantum algorithms that explore weight space in quantum superposition. Rather than updating network weights one gradient step at a time, quantum training algorithms might explore multiple gradient directions simultaneously, potentially finding optimal network configurations that would be invisible to classical training methods. Consider the extraordinary optimization challenges facing climate modeling and weather prediction. These systems involve nonlinear interactions between atmospheric, oceanic, and terrestrial processes that span multiple scales of time and space. Classical climate models must make approximations that limit their precision, But quantum algorithms could potentially simulate these complex systems with greater fidelity, leveraging quantum parallelism to explore multiple possible climate futures simultaneously. Financial markets present another fascinating domain for quantum optimization. Portfolio optimization, risk analysis, and algorithmic trading all involve computational problems that grow exponentially with the number of assets and constraints involved. Quantum algorithms could potentially explore vast portfolios in superposition, finding optimal risk-return balances that account for correlations and dependencies that would overwhelm classical optimization methods. The quantum advantage in optimization often emerges from the ability to escape local minima through quantum tunneling effects. Classical optimization algorithms can become trapped in suboptimal solutions, like hikers who reach a false summit and can't see the higher peaks beyond. Quantum optimization algorithms can tunnel through energy barriers, exploring solution landscapes that would be inaccessible to classical methods. There is something almost philosophical about the way quantum optimization mirrors the creative process itself. Just as human creativity often involves making unexpected connections and leaping across conceptual chasms, quantum algorithms can make computational leaps that seem to transcend the logical stepwise progression of classical optimization. They don't just find better solutions, they find solutions in fundamentally different ways. The development of quantum optimization algorithms represents a beautiful convergence of theoretical computer science and practical problem solving. Quantum annealing systems, like those developed by D-Wave, attempt to find optimal solutions by slowly cooling quantum systems toward their ground states. Variational quantum algorithms use quantum classical hybrid approaches that leverage the best aspects of both computational paradigms. As we drift toward sleep, contemplating the vast optimization challenges that shape our interconnected world, we can appreciate the profound potential of quantum algorithms to find better pathways through the computational forests that surround us. These algorithms don't just optimize faster, they optimize differently, exploring solution spaces that classical computers cannot access. And in this gentle exploration of optimization dreams, where quantum algorithms learn to navigate computational landscapes with the fluid grace of quantum tunneling and superposition, we glimpse perhaps the most beautiful aspect of quantum optimization. It reveals that the most difficult problems often have elegant solutions hiding in the quantum realm, waiting for us to develop the computational vision to perceive them. The quantum computer doesn't just solve optimization problems, it dreams new solutions into existence. As we approach the gentle conclusion of our quantum journey, we find ourselves standing at the edge of a vast computational horizon where the dreams of quantum computing meet the practical realities of current technology, and where the infinite possibilities of quantum mechanics stretch out before us like an ocean of unexplored potential. Tonight, we drift into contemplation of where quantum computing stands today and the breathtaking visions of tomorrow that shimmer just beyond our current reach. Picture, if you will, the current state of quantum technology as a delicate seedling pushing through the soil of classical computation, fragile, promising, but still vulnerable to the environmental challenges that surround it. Today's quantum computers are remarkable achievements of human ingenuity, but they remain in what researchers call the NISQ era, noisy intermediate-scale quantum devices that can perform quantum calculations but lack the error correction needed for truly transformative applications. These current quantum computers are like the first automobiles at the turn of the 20th century, clearly revolutionary in their potential, but still prone to breaking down, requiring specialized expertise to operate, and useful primarily for demonstrating possibilities rather than replacing existing transportation infrastructure. Google's quantum supremacy demonstration, IBM's cloud-accessible quantum processors, and the growing ecosystem of quantum startups represent humanity's first tentative steps into the quantum computational territory that will likely define the next century of technological development. Yet this is only the beginning of quantum computing's deeper trajectory, the roadmap toward fault-tolerant quantum computers, systems with millions of error-corrected qubits capable of running quantum algorithms for hours or days without decoherence, stretches across decades of continued scientific and engineering advancement. These future systems will require breakthrough developments in quantum error correction, qubit fabrication, control electronics, and classical quantum interfaces that we can envision conceptually but have yet to achieve practically. There is something both humbling and inspiring about the challenges that remain. Building a fault-tolerant quantum computer capable of breaking RSA encryption or simulating complex molecular systems requires not just scaling up current technology, but solving fundamental problems in quantum physics and engineering that push the boundaries of human knowledge. It's like attempting to build a cathedral when we've only recently learned to stack stones. Possible in principle, but requiring decades of patient craftsmanship and accumulated wisdom. Meanwhile, across the gentle landscape of near-term quantum applications, we see promising signs of quantum advantage emerging in specialized domains. Quantum chemistry simulations, optimization algorithms, and machine learning applications are beginning to demonstrate quantum speed-ups on current noisy devices, suggesting that useful quantum computing might arrive gradually rather than through sudden revolutionary breakthrough. The vision of a quantum internet represents perhaps the most ambitious and beautiful extension of quantum computing technology. Imagine, if you will, a global network where quantum entanglement links quantum computers across continents, creating a cosmic web of quantum correlation that enables unprecedented levels of computational coordination and cryptographic security. In this quantum internet, entangled photons would carry quantum information through fiber optic networks. Quantum repeaters would extend entanglement across arbitrary distances, and distributed quantum algorithms could harness the computational power of quantum computers worldwide. This quantum internet wouldn't simply make our current internet faster. It would enable entirely new forms of information processing that leverage the non-local correlations of quantum entanglement. Distributed quantum sensing networks could achieve measurement precision that surpasses what any individual quantum sensor could accomplish. Quantum cloud computing could allow users to access quantum computational resources as easily as we currently stream videos or download files. There is something profoundly poetic about the idea of information traveling instantly across the quantum internet through entanglement, not limited by the speed of light that constrains classical communication, but transcending space itself through the mysterious correlations that quantum mechanics allows. It's as if we're building a nervous system for the planet that operates according to quantum rather than classical principles. As we contemplate these quantum futures, we must also acknowledge the profound philosophical implications of widespread quantum computing adoption. If quantum computers can simulate molecular systems with perfect accuracy, if quantum optimization algorithms can solve planning problems that are impossible for classical computers, if quantum machine learning can discover patterns in data that remain invisible to classical analysis, then quantum computing doesn't just represent faster computation, but fundamentally different ways of understanding and interacting with reality. The quantum computer challenges some of our most basic assumptions about the relationship between information and physical reality. It suggests that computation itself might be more fundamental than we previously understood. Not just something we do with matter and energy, but something that matter and energy do naturally as they evolve according to quantum mechanical laws. Consider the beautiful possibility that quantum computers might help us understand consciousness itself. If consciousness emerges from quantum processes in biological systems, as some theories suggest, then quantum computers might provide the first artificial systems capable of experiencing quantum mechanical phenomena in ways that resemble biological cognition. There is something deeply calming about contemplating these vast quantum possibilities while acknowledging that we stand at the very beginning of this technological journey. Like astronomers who have invented the telescope and glimpsed distant galaxies, but have yet to explore them, we can envision quantum computational territories that remain largely unmapped and unexplored. The development of quantum computing represents more than just technological advancement. It embodies humanity's ongoing conversation with the deepest mysteries of existence. Each quantum computer we build, each quantum algorithm we develop, each quantum protocol we implement brings us closer to understanding what it means to process information in a universe that appears to be fundamentally quantum mechanical. As we drift towards sleep, resting in the gentle contemplation of these quantum horizons, we can appreciate both how far quantum computing has come and how far it might yet travel. The quantum future approaches not as a sudden transformation, but as a gradual dawn where the impossible slowly becomes inevitable, where the dreams of quantum mechanics become the tools of human creativity. And in this final meditation on quantum possibilities, where current limitations dissolve into future potentials, and where the mathematics of quantum mechanics points toward computational territories that stretch beyond imagination, we glimpse perhaps the most beautiful aspect of the quantum future. It reminds us that we live in a universe of infinite computational possibility, where the boundaries between mind and matter, between information and reality, continue to blur in ways that our quantum ancestors could never have imagined. In the quantum realm, computation becomes contemplation, technology becomes philosophy, and the future remains forever a superposition of infinite, beautiful possibilities, waiting for us to observe them into existence.